Right, so I just wanted to say a little bit more about analytical techniques, and we've met some of these before. So we have met infrared spectroscopy, and so you might see a spectrum which looks a little bit like this. So remember, up the side here we've got often percentage transmittance, and then along the bottom this is wave number. So here we've got 500 and that goes to 4000, so the scale is backwards. And then here we have these peaks. Remember, you can look on your data sheet to see which types of bonds these correspond to. So infrared looks like this and tells you about bonds. I often think it's a good idea to be aware of 4 particular bonds, just because then you can more quickly look at the spectrum. So a peak pretty much bang on 3000 is a CH. And that's only useful to allow you to differentiate between a CH and an OH. So here the CH has actually got swallowed up by this peak here, which is an OH. So OH peaks tend to be broad and they're around 3000. Some slightly higher, some slightly lower, depends on what type of group they are part of. So this distinctive peak here is normally around 1700 or 1750, is a C double bond O, and that's quite an easy one to spot. So this area here is busy, so from about 1500 down is what we call the fingerprint region, because you can see it's a busy region. So this is unique to one particular molecule, and you'd compare your spectrum to a database to try and identify exactly which molecule you have. But in there, there's often, and here I suspect it's that one, a peak at around 1100, 1200 for a C single bond O. Now there are other peaks which are useful, but as I said, I just think it's handy to have those 4 in mind to allow you to look and see which peaks are there and which peaks aren't there, which will often give you a clue in the question. So if you're not sure of that, go back and have another look. That's just a quick overview. So this is infrared, which tells you about what bonds you've got. So next up, we've also previously had a look at mass spectrometry. And so this is our mass spectrum, so more of a kind of graph with peaks on it. So this is relative abundance, which is essentially how much you've got of each peak, which doesn't really tend to matter very much for us. Along the bottom, this is M over Z, which they often write as the mass to charge ratio. So M stands for mass, Z is the charge of the ion, which we assume is +1. So in mass spectrometry, essentially mass spectrometry that it kind of does 2 things. It counts and it weighs. So it weighs different ions and it counts how many of them there are. And we're particularly interested in their mass. So the peak furthest to the right, so in this one I'd probably pick this one, is what's called the molecular ion peak, and that's the molecule as an ion with a charge of +1. These other peaks would be fragment ions, and often we look at the difference in mass between our molecular ion peak and our fragments to work out what's fallen off to help me build up a picture of the structure of my molecule. So mass spectrometry tells you about the mass. I'm going to introduce another couple of methods which we haven't done yet but which are coming up. So the next 2 methods are both NMR, which stands for nuclear magnetic resonance, and these spectra look very dull. So you have just a line at the bottom, and it's kind of this symbol, and then it says ppm. So this is a symbol for chemical shift in ppm, and on this one our scale goes from 0 to 220. This is carbon-13 NMR. And this happens to be the carbon-13 NMR spectra of propan-1-ol. But you can see the spectrum's very boring, as it were. You just get lines. So a couple of just single strong lines for carbon-13 NMR. So we'll come back on and I'll tell you how to interpret it. But basically, the clue's in the name. Carbon-13 NMR tells you about carbons in your molecule. And then we've also got what we call Proton NMR, which looks similar. You've got a scale at the bottom. Again, this is chemical shift in ppm, parts per million. It goes from 0 up to about 8 or 9, sometimes 10. This one, again, our scale is backwards for historical reasons. And this type of NMR tells us about the hydrogens in a molecule, and we'll spend quite a long time doing this because it tells you an awful lot about your molecule. It's one of the most powerful analytical techniques. So we'll come back to that one. Okay, so that was a brief overview of the different types. Just want to come back to mass spectrometry. So we've met mass spectrometry before. I don't know if you can see on the video or not, but for example, this number says 869.50580. So this is what we call a high resolution mass spec. So instead of all the masses being just to whole numbers, you can see they can actually be given to 3 decimal places. That's because we have a tendency to round up the masses of atoms. But we don't have to. So when you have a high resolution mass spectrometry machine, you can work out the masses to 4 or 5 decimal places. And so molecules which would have the same whole number, MR, so for example, I think low resolution, so to the nearest whole number, carbon monoxide and nitrogen, N2, both have a molecular weight of 28 to the nearest whole number. But if you can do a high resolution mass spec, you can get their masses to 4 or 5 decimal places, and you will find that they are actually different. So you can identify your molecule very accurately. Usually you would work out, find the molecular ion peak mass to 4 or 5 decimal places and then compare it to a database. So questions in the exam usually just ask you a little bit about that.